This is Edward Moorehead with the Unit 4 mid-unit assignment. So starting with 4, the regular motion of the Earth around the Sun causes a daily change in the high temperature of any location on Earth. The chart and graph show the average daily high temperature in degrees Celsius for each month in Yellowknife. The Northwest Territories compiled for several years. Determine the trigonometric equation that models this information. Let y be the temperature in degrees Celsius and x be the numerical value of month. So, to determine this, the lowest temperature is negative 24 degrees Celsius in January, and the highest is 21 degrees in July. So we get y equals a cosine k to the x minus d plus c. So then for a, we take the max and the minimum and divide by 2, which gives us 22.5. For k, we take 2 pi divided by the period, which gives us pi over 6. For d, it's just 1. And then for c, we get 21 plus 24, negative 24 over 2, which then gets us 1.5. Therefore, y equals negative 22.5 cosine pi over 6 x minus 1 minus 1.5. Then, for 2, a Ferris wheel has a diameter of 10 meters and takes 24 seconds to make 1 revolution. The lowest point on the wheel is 1 meter above the ground. So sketch a graph to show how a rider's height above the ground varies with time as the Ferris wheel makes a rotation. Assume the person starts the ride at the lowest point on the wheel. So, in this graph, you see at 0 seconds, the person starts at 1 meter, and then it goes up to 11 meters. Eventually, at 24 seconds, they return at 1 meter. B, where h times t is the height of the tide. Write a trigonometric equation that describes the graph. So y equals negative 5 cosine pi over 12 times x plus 6. The way I got this was a equals 11 minus 1 over 2, which became 5. K equals 2 pi over 24, which became pi over 12. And c was 11 plus 1 divided by 2, which became 6. Check the accuracy of your equation by using t equals 12 seconds. Explain why this provides a check of the accuracy of the equation. What are 2 more values that would provide a good check? So, y equals negative 5 cosine pi over 12 times 12 plus 6, which would equal 11, the maximum height. So thus t equals 12 seconds is a good check because the rider should be at the maximum height after 12 seconds. 2 other good checks are 24 seconds, the minimum height, and 36 seconds, the maximum height again. So then question 3. The height of the tide in Bay of Fundy relative to the pier varies from a low of 4.5 at 2:08 to a high of 17.3 meters at 8:21, measured with the 24-hour clock. So before anything, I changed 2:08 to 2.13 hours and 8:21 to 8.35 hours. So A, assume the height of the tide can be modeled as cosine function of the time of day, and then determine the equation in the form height ht equals a cosine k td plus k t minus d plus c, and b, where height is the height of the where ht is the height of the tide in the pier in meters, and t is the time of day in hours. So for A and B, I did them together, which became A equals max minus min divided by 2, which became 6.4. K is 2 pi divided by 24 hours, which became pi divided by 12. D is 208 or 31 divided by 15. C is 17.3 plus 4.5 over 2, or 10.9. So the period is 8.35 minus 2.13 x2, which would equal 12.44, becomes k equals 2 pi over 12.44, and ht equals negative 6.4, 2 pi divided by 12.44, times t minus 2.13 plus 10.9. C. Determine the height of the tide relative to the pier at 11:30. Give your answer to the nearest 0.1 meter. So the height at 11.5 is equal to negative 6.4 cosine 2 pi over 12.44 times 11.5 minus 2.13 plus 10.9, which would equal 10.8 meters. And then D, a boat needs a depth of at least 12 meters to dock at the pier. Use a graphical approach to determine when the boat is able to dock and when it must leave. So here on my graph, looking at the graph, the boat can dock between approximately 5:30 a.m. to 11:30 a.m. Since that is when the tide will be higher than 12 meters, the boat will have to leave around noon. And as we can see from the graph, it starts around 5:30 and then goes to 12. No, sorry, it then goes to around 17 and then goes back to around 5:30 meters.